The Hidden Reality by Brian Greene. Picture this. You're standing between two mirrors, mesmerized by that endless tunnel of reflections stretching back into what seems like forever. When Brian Greene was a kid, he'd stand in his closet doing exactly this. He'd watch the cascade of his own images, each one a silent echo of the last, and imagine one of those distant reflections deciding to do something completely different, creating a whole new reality for all the reflections that followed. It sounds like a playful childhood daydream, right? But here's the thing. It touches on one of the most profound and reality-bending ideas in modern science. The possibility that our universe isn't the only one. That there are other worlds, parallel to our own, existing just beyond what we can see or touch. And no, this isn't science fiction. This is the world of The Hidden Reality, a book that has guided millions to the very edge of what we know about the cosmos. Brian Greene isn't just any physicist. He's a professor at Columbia University, one of the world's leading experts on string theory, and honestly, he's a master storyteller. His previous book, The Elegant Universe, became a global phenomenon, selling millions of copies and making complex physics accessible to everyone. In The Hidden Reality, Greene tackles his most ambitious subject yet. He asks a question that might sound crazy at first. What if everything we see, every star, every galaxy, the entire night sky, is just one tiny bubble in a vast cosmic ocean of other universes? Now, you might think this sounds like wild fantasy, but here's where it gets interesting. Greene shows us that this idea emerges naturally from our most successful and rigorously tested theories. From cosmology, from quantum mechanics, from string theory. When we follow the mathematics of our most trusted physical laws to their logical conclusions, we keep running into the multiverse. Over the next few minutes, we're going to embark on that journey together. I'm going to share with you the 9 different kinds of parallel universes that Greene explores, each one stranger and more wonderful than the last. Here's my promise. By the end of our time together, you'll not only understand these incredible ideas, but you'll also see the universe, and your place in it, in a completely new light. You'll understand why the possibility of parallel worlds isn't just a philosophical game, but a question that lies at the very heart of modern physics. So let's begin our journey into the hidden reality. Our journey starts with a simple, yet staggering thought. Look around you. Everything you can see, touch, and feel is made of particles, atoms, electrons, quarks. Now imagine you have a box of Legos. There are only so many ways you can arrange those Legos before you start repeating patterns. The universe works in a similar way. There are a finite number of ways particles can be arranged in any given volume of space. Now here's the twist. What if space itself is infinite? What if it just goes on forever? If you have an infinite amount of space, but only a finite number of ways to arrange particles within any patch of it, then the laws of probability say something extraordinary must happen. Patterns must repeat. It's not a possibility, it's a statistical certainty. This leads us to our first multiverse, what Greene calls the quilted multiverse. Far out in the cosmos, so far that light from there hasn't had time to reach us since the Big Bang. There must be another region of space, another patch in this cosmic quilt, where the particles are arranged in exactly the same way they are here. Think about what that means. It means there's another Earth, with another version of your house, and inside that house is a person who is physically identical to you in every single way. A perfect copy. Your doppelganger. Right now, they might be listening to these very words, feeling the same curiosity you are. And it doesn't stop there. In an infinite space, there isn't just one copy. There are infinitely many. In some of these parallel worlds, your copy is making slightly different choices. Maybe they decided to pursue that passion you let go of. Maybe they took that trip you always dreamed of. Every possible version of your life, every path you could have taken, is being played out somewhere in the quilted multiverse. This idea is both humbling and exhilarating. It suggests that reality is a vast tapestry, and our entire observable universe is just one small pattern, repeated over and over across an infinite expanse. But it's also the simplest of all the multiverse theories, because it relies on just two assumptions: that space is infinite, and that there are a finite number of ways to arrange matter within it. But this is just the beginning. Our next stop takes us back to the very first moments of creation, to a theory that has become the cornerstone of modern cosmology: inflation. For decades, scientists were puzzled by a mystery known as the horizon problem. When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, we see that it has an incredibly uniform temperature everywhere in the sky. The temperature in one direction is 2.725 degrees above absolute zero, and in the opposite direction, it's the same, to an astonishing precision. This is deeply strange. These two regions of the sky are so far apart that there hasn't been enough time in the 13.7 billion-year history of the universe for them to have ever been in contact, not even to exchange heat and even out their temperatures. It's like finding two people on opposite ends of the Earth who have never met, yet are wearing the exact same outfit, down to the last thread. How could this be? In the early 1980s, a physicist named Alan Guth proposed a radical solution. He suggested that in the first fraction of a second after the Big Bang, the universe underwent an incredible growth spurt, an exponential expansion called inflation. Space swelled at a rate far faster than the speed of light, stretching a region smaller than an atom to a size larger than the entire observable universe today. This solves the horizon problem because, before this burst of expansion, all these regions of space were in close contact. They had plenty of time to reach a uniform temperature, like a well-mixed cup of coffee. Then, inflation suddenly blew them apart to cosmic scales, preserving that uniformity. Inflationary theory has been incredibly successful. Its predictions, especially the tiny temperature ripples it forecasts in the cosmic microwave background, have been confirmed by observation with stunning accuracy. But here's where it leads to our second multiverse. Theorists like André Linde realized that the mechanism driving inflation is likely not a one-time event. It's more like a chain reaction that never truly stops. Imagine the universe as a vast, bubbling pot of water. Our universe could be just one bubble that formed when a small region of space stopped inflating and cooled down, allowing matter and galaxies to form. But outside our bubble, the oxy, water, is still boiling. The inflationary process continues, constantly spawning new bubble universes, each one potentially infinite in its own right. This is the inflationary multiverse. Our universe becomes one of countless holes in an ever-expanding block of cosmic Swiss cheese, with each hole being a self-contained cosmos, possibly with its own unique properties. What's truly mind-bending is that Greene shows how these two multiverses are connected. Each bubble universe in the inflationary multiverse, when viewed from the inside by its inhabitants, would appear to be spatially infinite. This means that every single bubble in the inflationary multiverse would also contain its own quilted multiverse of repeating worlds. It's a multiverse of multiverses. So far, we've been exploring the vastness of space. But what if there's more to reality than the dimensions we know? This question leads us to the world of string theory, and to three more kinds of parallel universes. String theory is our most ambitious attempt to create a unified theory of physics, a single mathematical framework that describes all of nature's forces, from gravity to electromagnetism. Its central idea is simple and beautiful. If you could zoom in on the fundamental particles that make up our world, electrons, quarks, and so on, you wouldn't see tiny dots. You would see that each particle is actually a tiny vibrating filament of energy, a little string. Just like the strings on a violin can vibrate in different patterns to produce different musical notes, these fundamental strings can vibrate in different patterns to produce different kinds of particles. The vibration that creates an electron is different from the one that creates a quark, which is different from the one that creates a photon, In this view, all the rich diversity of the universe is just a symphony played on these tiny vibrating strings. But for the mathematics of string theory to work, it requires something extraordinary. The universe must have more than the 3 spatial dimensions we experience. In fact, the theory demands a total of 10 spatial dimensions. So, where are these extra dimensions? The idea, going back to the 1920s, is that they might be curled up into tiny, intricate shapes, so small that we can't detect them. Imagine a garden hose. From far away, it looks like a one-dimensional line. But if you get close, you see it has a second, circular dimension curled around it. String theory suggests that at every point in our familiar 3-dimensional space, there are 6 extra dimensions, curled up into a complex shape known as a Calabi-Yau manifold. This idea of extra dimensions opened up a whole new way of thinking about reality. In the mid-1990s, string theorists discovered that the theory didn't just contain one-dimensional strings. It also contained higher-dimensional surfaces called branes, short for membranes. This led to a radical new picture of our universe. What if our entire 3-dimensional cosmos isn't all there is? What if it's just one giant brain, like a single vast slice of bread, floating in a higher dimensional space, the cosmic loaf? This is the brain multiverse. There could be other brains, other universes, floating parallel to ours, perhaps just a microscopic distance away in another dimension. We're trapped on our own brain, like ants on the surface of a leaf, unable to perceive the other leaves floating nearby. Almost all the particles and forces in our universe are made of open-ended strings, whose ends are permanently stuck to our brain. We can't leave. Light can't leave. That's why we can't see these other worlds. But there's one exception: gravity. According to string theory, the particle that transmits gravity, the graviton, is a closed loop of string. It has no endpoints to get stuck, so it's free to travel between the branes. This suggests that gravity might be our only window into these other universes. This idea has led to real, testable predictions. For example, if gravity can leak into these extra dimensions, it would explain why it appears so much weaker than the other forces. Experiments at places like the Large Hadron Collider are actively searching for signs of this leakage, such as energy disappearing from collisions into other dimensions. If they find it, it would be powerful evidence for the brain multiverse. The idea of moving brains also gives rise to another possibility, the cyclic multiverse. What if 2 of these brain universes weren't just floating peacefully? What if they were moving toward each other, destined to collide? Theorists like Paul Steinhardt have proposed that such a collision would be a cataclysmic event, a big splat, that would wipe out everything on both brains and release a massive burst of energy, creating a hot, dense fireball. This sounds a lot like a Big Bang. In this model, the Big Bang wasn't the beginning of time, but just one event in an eternal cycle of collisions. The brains collide, bounce apart, expand and cool for trillions of years, long enough for galaxies, stars, and even life to form, and then, drawn back together by gravity, they collide again, resetting the cycle. Our universe would be just one chapter in an endless cosmic story, with parallel universes existing not in space, but in time, in the cycles that came before us and the ones that will come after. Now we come to perhaps the most controversial and powerful idea to emerge from string theory, the landscape. For a long time, string theorists hoped that the theory would uniquely predict the shape of the extra dimensions. They hoped there was only one correct Calabi-Yau shape, and that from it, they could calculate all the fundamental constants of nature, like the mass of the electron and the strength of gravity. But the opposite turned out to be true. Researchers discovered that there isn't just one possible shape for the extra dimensions. There isn't 1,000. There isn't 1,000,000. The mathematics of string theory allows for an astronomical number of different possible shapes, something on the order of 10 to the power of 500. That's a 1, followed by 500 zeros. Each of these shapes would correspond to a universe with a different set of physical laws and constants. This vast collection of possible universes is known as the landscape multiverse. At first, this was seen as a huge failure for string theory. If the theory allows for so many possibilities, how can it ever make a concrete prediction? But then, physicists realized this might be a feature, not a bug. It might be the key to solving one of the deepest mysteries in all of cosmology, the value of dark energy. In 1998, astronomers made a shocking discovery. They found that the expansion of the universe isn't slowing down, as everyone had expected due to gravity's pull. It's speeding up. Something is pushing space apart, an anti-gravity force that we now call dark energy. When physicists tried to calculate the amount of this energy, they got a result that was spectacularly wrong, off by a factor of 10 to the power of 120. It's been called the worst prediction in the history of physics. But the landscape multiverse offers a startling explanation. What if the value of dark energy isn't a fundamental constant that can be calculated from first principles? What if it's just an environmental variable that changes from one bubble universe to another? Across the 10 to the power of 500 universes in the string theory landscape, the amount of dark energy would vary wildly. In most of them, the value would be enormous, causing space to expand so violently that no galaxies or stars could ever form. In others, it might be strongly negative, causing the universe to collapse on itself in an instant. Life as we know it could only exist in those rare universes where, by sheer chance, the value of dark energy is incredibly small. Small enough to allow galaxies to form over billions of years. This is called the anthropic principle. We find ourselves in a universe with this strangely fine-tuned value for dark energy. For the same reason, we find ourselves on a planet with a life-supporting temperature. If things were any different, we wouldn't be here to ask the question. This is a deeply controversial idea. Some see it as a profound explanation, while others see it as a surrender, a just so story that gives up on the dream of a truly predictive theory. But it highlights the powerful synergy between inflationary cosmology and string theory, suggesting that the vast number of bubble universes from inflation might be the very places where all the different possibilities of the string theory landscape are physically realized. So far, we've journeyed through the cosmos, but our next multiverse takes us to the inner world of atoms and particles. It's perhaps the oldest, and, to some, the most compelling of all parallel universe theories, the quantum multiverse. Quantum mechanics, our theory of the microscopic world, is built on probability. When we describe an electron, for example, we can't say it's in one specific place. We can only describe it with a probability wave, which tells us the likelihood of finding it here or there or over there. But what happens when we actually make a measurement? When we look, we always find the electron in one, and only one, definite location. The range of possibilities seems to collapse into a single reality. For decades, physicists were puzzled by this. What causes the collapse? And what happens to all the other possibilities? In the 1950s, a young graduate student named Hugh Everett III proposed a breathtakingly simple and radical answer. He said, "The wave never collapses. All the possibilities happen. Every time a quantum measurement is made, reality splits. The universe branches into multiple parallel versions of itself. In one universe, you find the electron at location A. In another, identical universe, a copy of you finds the electron at location B. In yet another, a third you finds it at location C. According to this many worlds interpretation, there's no such thing as a road not taken. Every choice, every quantum event, from the decay of a radioactive atom to the firing of a neuron in your brain, causes reality to branch. This means there's a universe where you took that job, a universe where you married your high school sweetheart, a universe where you woke up 5 minutes earlier this morning. Unlike the other multiverses, these parallel worlds aren't separated by vast distances in space or hidden in other dimensions. They're all around us, constantly branching off from our own reality, but completely and permanently inaccessible to us. Once the split occurs, the worlds are decoherent. They can no longer interact. To its supporters, the quantum multiverse is the most elegant solution to the measurement problem. It requires no new physics, only that we take Schrödinger's equation, the central equation of quantum mechanics, at its word and apply it to everything, including ourselves. To its detractors, it's an outrageously uneconomical theory, postulating an infinite number of unseen worlds just to explain what happens when we look at an atom. The debate continues to this day, but it shows how deeply the idea of parallel realities is woven into the very fabric of our most fundamental theory of nature. Now prepare for what may be the strangest idea of all. What if our reality isn't the fundamental reality at all? What if everything we experience, our three-dimensional world, our lives, our thoughts, is just a projection, a hologram? This idea, known as the holographic multiverse, comes from some of the deepest thinking about black holes and the nature of information. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking made a startling discovery. They found that the amount of information a black hole can contain, its entropy, isn't proportional to its volume, as you might expect. It's proportional to the surface area of its event horizon, the boundary of no return. It's as if all of the information about what fell into the black hole is somehow stored on its two-dimensional surface, not within its three-dimensional interior. This led Gerard T. Hooft and Leonard Susskind to propose a radical idea, the holographic principle. They suggested that this might not just be a property of black holes, but a fundamental principle of the universe itself. The principle states that all the information needed to describe a three-dimensional volume of space can be fully encoded on a two-dimensional surface that surrounds it. What does this mean? It means that our three-dimensional reality might be an illusion. The real, fundamental physics might be happening on a distant, two-dimensional boundary surface, and everything we see and experience is just a holographic projection of that physics. Imagine a 3D image projected from a 2D holographic plate. The plate itself looks like a meaningless scramble of light and dark patterns, but when light shines on it correctly, it produces a rich, three-dimensional world. The holographic principle suggests our universe is like that. There's a parallel reality, a universe, playing out on a distant, flat surface, and we're its three-dimensional projection. This idea found stunning mathematical support from string theory. In 1997, Juan Maldacena discovered a concrete mathematical example of this duality. He showed that a particular theory of strings and gravity in a five-dimensional curved spacetime was completely equivalent to a simpler, non-gravitational quantum field theory living on its four-dimensional boundary. The two theories looked completely different, but they were mathematically identical, a perfect dictionary for translating between the bulk world and the boundary world. This doesn't prove that we're a hologram, but it shows that the idea is mathematically coherent. It suggests the existence of a parallel universe that's not just separate from ours, but is, in a deep sense, a more fundamental description of it. Our final two multiverses take us from the frontiers of physics to the realms of philosophy and computation. With the relentless growth of computing power, it's not hard to imagine that one day, our descendants will be able to create incredibly realistic computer simulations, worlds so detailed that the beings living inside them would be self-aware and would believe their world was real. This is the simulated multiverse. The philosopher Nick Bostrom famously argued that if it's possible to create such simulations, it's almost certain that we're living in one. The reasoning is simple. A real, base reality civilization would likely create billions or trillions of simulated universes. Therefore, the number of simulated beings in existence would vastly outnumber the number of real beings. If that's the case, simple statistics suggest that any given conscious being, including you, is overwhelmingly likely to be one of the simulated ones. In this scenario, our universe is a piece of software running on some advanced being's computer. Our laws of physics are just lines of code. This is a humbling and somewhat unsettling thought, but it also represents a multiverse of a completely different kind, a vast collection of artificial worlds, each a parallel reality created with purpose. Finally, we arrive at the most expansive and abstract multiverse of all, the ultimate multiverse. This idea, championed by thinkers like Max Tegmark, takes the connection between physics and mathematics to its ultimate conclusion. Physicists have often marveled at the unreasonable effectiveness of mathematics in describing the universe. Why should the abstract world of equations map so perfectly onto the physical world? The ultimate multiverse proposes a radical answer. It's because mathematics is the physical world. The idea is that every mathematically consistent structure, every possible set of equations, describes a real, physical universe. Our universe seems special to us only because we're in it, but in the grand scheme of things, it's just one entry in a vast library of all possible mathematical realities. This is the multiverse of all possible universes. Any universe you can imagine, as long as it's logically consistent, exists somewhere in this ultimate ensemble. A universe with different laws of physics? It's there. A universe made of mozzarella? If you can write down the math for it, it's there too. This idea solves the ultimate why question. Why is our universe governed by these particular laws? The answer is, it isn't special. All possible laws are realized in some universe. We just happen to find ourselves in one that's complex enough to support life. From the quilted cosmos to the ultimate library of Babel, we've journeyed through 9 distinct visions of parallel realities. Each one pushes the boundaries of our imagination, and each one stems from our most serious attempts to understand the universe. They remind us that reality may be far grander, stranger, and more magnificent than we ever dreamed. As we come to the end of this incredible journey through the hidden reality, it's natural to feel a sense of awe and perhaps a bit of dizziness. The idea of 9 different kinds of multiverses, each one more mind-bending than the last, can be overwhelming. But what I find most powerful about Brian Greene's work isn't just the what, but the why. These ideas aren't born from wild speculation. They're the logical consequences of our most successful scientific theories. When we take the mathematics of cosmology, quantum mechanics, and string theory seriously, when we follow the equations wherever they lead, we find ourselves staring at the possibility of parallel worlds. It's as if the universe itself is trying to tell us that it's far larger than we ever imagined. This fits into a long and noble pattern in the history of science, a pattern that we might call the Great Copernican Demotion. For centuries, we believed we were at the center of everything. Copernicus showed us that the Earth isn't the center of the solar system. Later, we learned our sun is just an ordinary star on the outskirts of a typical galaxy, the Milky Way. Then we discovered that our galaxy is just one of hundreds of billions in the observable universe. And now, the multiverse concept suggests the final demotion. Our entire universe may be nothing special, just one of countless others. Each of these steps felt like a loss of importance, but each one ultimately gave us a truer, grander, and more beautiful picture of our place in the cosmos. The multiverse may be the ultimate expression of that, the realization that we're part of a reality so vast and rich that it defies our everyday intuition. But this raises a crucial question, one that Greene tackles head-on. Is this still science? If these other universes are forever beyond our reach, how can we ever test these ideas? Science, after all, is built on testable predictions. Greene's answer is subtle and profound. He argues that even if we can't visit these other worlds, multiverse theories can be testable. A theory might predict that all universes in the multiverse share certain common features, or that there are specific correlations between properties. For example, a multiverse theory might predict that any universe with electrons must also have another, yet undiscovered particle. If we search for that particle in our universe and don't find it, we can rule out the theory. The multiverse idea, in many of its forms, isn't a free-for-all. It makes specific, falsifiable claims. The most powerful takeaway from the hidden reality is the invitation to expand our definition of what is real. It challenges us to trust in the power of mathematics and human reason, to guide us into realms that our senses may never reach. It reminds us of Newton's beautiful words, that we're like children playing on the seashore, picking up a smoother pebble here and a prettier shell there, while the great ocean of truth lies all undiscovered before us. This book is a courageous voyage out into that ocean. That was a summary of The Hidden Reality by Brian Greene. We've explored the highlights today, but I'll be honest with you, a summary can only take you so far. The real magic happens when you read the book yourself. It's in the quiet moments, when Greene's elegant prose and brilliant analogies make a truly difficult concept click into place in a way you didn't expect. This summary is designed to help you decide if this book is worth your time and curiosity. If anything we've talked about today has sparked your imagination, grab a copy. Reading it isn't just about learning facts about the universe. It's an experience that can genuinely change the way you see reality itself. A link to the book is in the description below. Also, if you found this journey valuable, please take a moment to hit that like button and subscribe to the channel. It tells us that these deep dives matter to you, and ensures you won't miss our next exploration into another life-changing book from the billionaire's bookshelf. Let's keep opening our minds and growing together.